Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to part 8 of nuclear magnetic resonance spectroscopy. Let us test our knowledge on the NMR we gained so far from the previous lectures. Select the approximate chemical shift for each of the hydrogens in the proton NMR spectrum of isopropyl butyrate 0.9, 1.3, 1.79, 2.32, and 4.93. Assuming first order rules apply, specify the multiplicity and relative intensity of the peaks for each of the resonances. زي ما قلنا قبل كده الأرقام أحتفظ بيها في الميموري بحل أسئلة كتير لكن ما بقعدش أحفظ. اوكي، فهنا الشرط ادي قدامنا مثل جروب methylene protons and methane proton بيظهروا في الرينج from 0 to 2. If you have methylene adjacent to C double bond O, so it's ranged from 2 to 3. If you have the methylene proton adjacent to oxygen, then it's from 3 to 5. Having the structure of the isobutyl butyrate okay, we have mentioned that the methane here adjacent to oxygen then will be this one 4.9. You have CH2 adjacent to carbonyl, so it is 232. Okay, and 0.9 will be the C methyl group far away from the electron withdrawing groups, this one. And now you have methylene protons, that's most likely to be that one. And these two CH3s will be at 3.32. That's roughly from the chart. The other method we mentioned before, that you draw the structure on specific program, okay, and submit it asking for prediction of the proton NMR. Here is a ChemDraw, showed the methane at 4.92, and this is how the program make the calculations. 1 alpha OC double bond O, 2 alpha carbon, and general corrections. Okay, and this methyl group, it's here, the other CH3 in here. Okay, and the methylene protons, this one, and the other methylene protons, all right, that one. Now, what is the multiplicity of this peak? See, we have here 1H. So this CH3 and this CH3 are equivalent, and neighbor to them one hydrogen, it will show up as a doublet. But what about this hydrogen? This hydrogen is surrounded by 6. 6 plus 1 is 7, septet. So this one will show up as septet, 7 peaks. This methylene protons adjacent to CH2, so it will show up as triplet. Fine. This CH3 is adjacent to CH2. So it will be another triplet. Remember that we have here free rotation, right? This is carbon, single bond carbon. Because of the free rotation, the coupling constant between the hydrogen on this carbon and the hydrogen on that carbon will show up to these CH2 groups as equivalent. So 3 plus 2 is 5. So these CH2s will show up as 5 plus 1, 6, sextet. Show up as sextet. But why they are equivalent? As we mentioned before, we have free rotation. The free rotation of these hydrogens, as recall from the organic chemistry 1, the conformer and rotamers of alkane, you will have this conformer where the angle between the hydrogen is 60, and we call this is gauge, and the J value according to Carber's equation is from 2 to 5 Hertz. You have here the trans conformer or staggered conformer, and the angle is 180, and J value is from 10 to 16 Hertz. Another gauge in this cycle, okay, its angle is 60, and that's J3 is 2 to 5 Hertz. What about this one? This contribution can be null because it's unstable one. So we will have the contribution from 2 gauge and 1 trans. 2 gauge and 1 trans, average divided by 3, it's equal to 7 Hertz. Right? Do the same as you have done for part A and B, this time for 4,4 dimethyl cyclopentene to in 1 on 1.25, 2.9, 6.57 and 6.7 part per million. Specify whether the pair A and B are homotopic, enantiotopic, or diastereotopic. Do the same for the GEM method unit. Again, if we use the chart in front of us, you will find out that the methyl will be the lowest delta value, and that will be 1.25. This is methyl. Then the methylene protons showing up at 2.9, and now we have 2 olefinic protons. Which one will get the higher value? Okay. Looking for the resonance structure of alpha beta unsaturated carbonyl, we will find out that this carbon has a positive charge. Accordingly, this hydrogen will be more de-shielded than that one. طبعا عليها positive charge، هتحاول تسحب الالكترونات ناحيها عشان تعوض، يبقى صاحبتنا الهيدروجين دي de-shielded. Okay, and this hydrogen will get higher chemical shift 6.5, while this hydrogen will get the 6.07. What is the relation between these two hydrogens? They show up chemically equivalent. Okay, looking for a molecular model here, okay, you will find out that this ring is very close to be planar. Okay, and if you go, these two hydrogen are mirror image to one another. These two will be in this plane, okay, mirror image to one another. Let me do it this way, okay. So it's like plane, mirror image. They are mirror image to one another, so they are enantiotopic. They are enantiotopic regions. Provide a structure of a compound having a molecular formula C5H10O that consists with the following spectrum. From the IR, no peaks above 3000, which indicate no unsaturation. We have peak here at 16, 17. So we have carbonyl, but nothing in the range of 2700. So this is ketone. It's not aldehyde. Coming back, using the chart, and then we examine the spectrum. 0.9, 3 protons, triplet. Mean that we have CH3 adjacent to CH2. CH2, 2 plus 1 is 3. Right. We have this fragment. Now, we have at 1.6, 2 protons, 1, 2, 3, 4, 5, 6. That's sextet. Mean that we have CH2 adjacent to CH3, CH2. They are 5. 5 plus 1 is 6. Okay. We have another fragment at 2.1, 3 protons, mean that we have CH3, and then we have spin inactive adjacent to it, spin inactive nuclei. Carbon 12 here, and C double bond O هيديني المطلوب ان ال CH3 will appear as singlet 3 protons at 2.1 CH2 methylene adjacent to C double bond O. It's from range 2 to 3, and we have here 2.1. Okay, and the last peak is at 2.4 for 2 protons, and these 2 protons showing up as triplet, mean that you have CH2 adjacent to CH2, and the other side spin inactive nuclei. Remember that CH2 will need 2 bonds, carbon tetravalent, and we have only 2 hydrogens, then we need 2 bonds. One will be spin inactive, and the other one will be the CH2 group, اللي هي بتسبب ان دي تظهر ايه؟ triplet. Remember that from IR we have C double bond O. Alright, make a table, chemical shift, 0.9, integration, 3 protons, multiplicity, triplet, assignment that will be CH3 adjacent to CH2. 1.9, it's 2 protons, sextet means it's CH2 adjacent to CH3, CH2. 2.1, 3 proton, singlet, so it's CH3 adjacent to spin inactive. 2.4, 2 proton, triplets, so it's CH2. Then CH2 adjacent CH3, so H2, and another spin inactive on the other side. Getting these pieces together, C double bond O CH3, C double bond O CH2, 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 CH3, CH2, CH2, CH3, sum them together, this is a structure. Yes, that is a structure. Here is one more advanced problem. One NMR spectrum at 400 MHz in deuterochloroform was obtained from dimethyl cyclopropane dicarboxylate. Is it cis or a trans isomer? From my own experience, when I looked at spectrum like this is a first order. Okay? أنا بس بغششكوا ده يعني. Okay? This is first order. And this one seems like doublet of doublet. Right? And let me examine now the stereochemistry of the cis. And examining the stereochemistry of the cis and trans, here we have the cis isomer. I would like you to look here for a plane of symmetry. You will find out that these two hydrogens are mirror image to one another. So you have here X, X. You have here two hydrogens they are not related to one another by any symmetry operation. So you have here A and M, and you have AMX2 type with three different kinds of protons. يبقى هنشوف للمجموعة دي اللي هي ال AMX2 3 signals, 3 signals, while this here methyl أو methoxy group, the methyl ester, okay, OCH3, this OCH3 in here, and they will show up again mirror image to one another, the one signal singlet. Okay, if you look at the cis here, that's what I was talking about. Plane of symmetry, they are mirror image to one another, right? Hope it's clear. These two hydrogens are not related to one another. They are different. That's why you will see them, okay, MAM system, okay. Now if we switch to the trans isomer, in the trans isomer, then you will find C2X of symmetry. Okay, X from here to the back, switch. All right, you end up with the same molecule if you switch it, right? So you have X of symmetry as these two hydrogens are homotopic, and these two hydrogens are homotopic. X will go through this. Okay, C2X of symmetry 180, you find them the same. Okay, so if you have A, you have B, or a chemical shift far away from each other, then you will have A and X. But this hydrogen coupled to that one trans, and coupled to that one cis. So the system is A chemically equivalent but mechanically non-equivalent. So it's A prime, B prime, or if their chemical shift is far away from each other, it's A prime, X prime. In this case, you will see a little bit complicated spectra, but two signals. Each one is two hydrogens. Integration of two hydrogen intensity. In the cis isomer, you will find three signals, one intensity, one proton intensity, and the third one is two proton intensities. Go back to the spectrum. You will find that one of the protons triplet, and each one of them will be doublet, which will be 1 to 1 to 2 to 2 to 1 to 1. Since you have triplet 1 to 2 to 1, then each one will be doublet. So the 1 will be 1 1, 2 will be 2 2, 1 will be 1 1. See the spectrum? Very beautiful first order. The second one, just a minute please. So if you consider this proton will couple to these two protons equally, so it will form triplet, and then geminal hydrogen J2, this one to that one, to form the doublet again. Okay, this proton will be with these two protons, equivalent protons, will be triplet, and coupled to that one, to each triplet will be, each line of the triplet will be doublet. On the other hand, these protons will couple to that two protons, triplet, and then to this one, doublet. Hydrogen, B triplet first, 1 to 2 to 1, then each line will be 1 to 1, 2 to 2, 1 to 1. Okay, triplet of doublet. Now these two hydrogens will be doublet to that one and doublet to that one, so it will be doublet of doublet. Doublet, and then each one of these line will be here 1 to 1, and then as you can see it in here, it's 1 to 1 to 1 to 1 ratio, doublet of doublet. I hope you have gained the basics now and you are satisfied with your capability to analyze proton NMR spectrum. So dear, see you in the next lecture. Will be on the carbon-13 spectroscopy. Good luck.